Okay, so let's look at number systems, and the first thing I want to just mention is BIMDAS, the order of operations when we're trying to do long sums. Okay, and BIMDAS simply means that when we look at a sum like this one here, we look at the sum from left to right, and as we do, first we look for brackets and we fix what's in the brackets. Then we look for indices, powers, we look for multiplication signs, then we look for division, addition and subtraction, and we look from left to right in that order each time. So if you look at this example here, we have 2 plus 3 to the power of 2 plus bracket 6 divided by 2 close brackets plus 5 times 6. So if we're going to use the BIMDAS rule, the first thing we need to fix is what's in the brackets, and 6 divided by 2 is 3. So we rewrite the line. We have 2 plus 3 to the power of 2 plus 3 plus 5 times 6. Next thing we look for is the power, or the indices. That's what the I stands for. And we see that 3 to the power of 2 is 9, and we rewrite the sum again. Then we look from left to right to see if there's any multiplication signs, and yes, there's one here. So we deal with that next, and we rewrite 2 plus 9 plus 3 plus 30. And then I like to just be safe and do these two at a time. 2 plus 9 is 11. 11 plus 3 is 14, and 14 plus 30 is 44. And that's your answer to this long sum using the BIMDAS method, working from left to right, ticking off each of these as you meet with them. Next, let's look at factors. What are factors? Factors, otherwise known as divisors. They're those numbers which divide into a number evenly. So the factors of 20 are any numbers that divide into 20 evenly. Let's look at the factors of 12. Does 1 go into 12? Yes, goes in 12 times evenly. 2 goes into 12 6 times. 3 goes into 12 4 times. They are the factors of 12. The factors of 20, 1 goes into 20 evenly, 2 goes into 20 evenly, 3 doesn't go into 20 evenly, 4 does, 5 does as well, sorry, 4 5s does as well, and they are the all and only factors of 20. And in maths, we often heard back in first year that we had to look for the highest common factor of two numbers, and the highest common factor of 12 and 20, but we've listed the factor here. Let's look for the highest common factor, and the highest common factor of 12 and 20 is equal to 4. And where and why might we use that in maths? Well, we might have a problem where we need to simplify the fraction 12 divided by 20, and the best way to rewrite that in its simplest form, reduce it to its simplest form, is to divide above and below by the highest common factor of 12 and 20. So if we were to divide 12 by 4, which is the highest common factor, and 20 by 4, we get 3/5. So the fraction 12 over 20 reduced to its simplest form and or equivalent fraction is 3/5, and we derive this by dividing above and below by the highest common factor of 12 and 20, the numerator and the denominator. Let's just remind ourselves about with the term multiples. What are multiples? Well, the multiples of 6 are 6 times 1, 6 times 2, 6 times 3, 6 times 4, and so on. So the multiples of 6 are 6, 12, 18, 24, 30, 36, and so on. And the multiples of 3, then, therefore, 3 times 1 is 3, 6, 9, 12, 15. And we've used the lowest common multiple in maths before, where we've looked or sought to add or subtract fractions, where we had something like 1/3 plus 3/6, and to do that we looked for the lowest common multiple of 3 and 6, and that is 6, and we used that to help us solve our fraction problem. Okay, so we'll move on just to a quick mention of the different types of numbers that we meet with in maths. Well, there's a set n of natural numbers that we meet in maths, and these are all the whole positive numbers. So 1, 2, 3, 4, 5, 9, and so on. So I just noticed that should be a 3 there, 4, 3, 4, 5, 6, and so on. Okay. Then we have integers, and they're denoted by the letter Z. Okay, and Z is the set of whole positive and negative numbers. Okay, so minus 3, minus 2, minus 1, 0, 1, 2, 3, all the way up and all the way back. That would they all are considered to be integers. The natural numbers are the whole positive numbers. Integers are the whole positive and negative, the whole negative numbers. So actually, natural numbers are a subset of integers. Okay, and then we come across rational numbers. Rational numbers, otherwise known as indicative of ratios, or numbers expressed as a quotient, which is where we get the letter Q to represent the set of rational numbers. Rational numbers look like something like 4 over 5, okay? But 5 is also a rational number because 5 is the same as that quotient or that ratio of 5 over 1, okay? So I'm supposed to put some language on it. 3/8 is a rational number whose value expressed as a decimal has an ending. So if you were to type into your calculator 3 divided by 8 equals, you would get 0.375. This number terminates here. Okay? 2 over 11, or 2/11ths, is a rational number whose value expressed as decimal is repeating. Actually, it doesn't terminate at all. It just keeps going on 181818 forever. Okay? But it's still a rational number. Okay, in this case 3/8 terminates, this repeats. Both are rational numbers. Which brings us on to mention the set of numbers represented by the letter capital I, the irrational numbers, and these are numbers whose value are non-repeating and non-terminating. Okay, so if you were to put into your calculator to try and find the square root of 2, or the square root of 11, or the square root of 3, square root of 2, square root of 3, or pi, you'd see that the value the calculator would give you would be non-repeating and non-terminating, and just gone on forever with no set pattern. The pattern is irrational. Okay. You might recall actually that root 2 and root 3 are also known as surds, okay, and you'll meet with surds in another chapter. We're just defining the different types of numbers here, and so we'll move on then. Prime numbers, small p, these are the positive integers, okay, that positive whole numbers that have only 2 divisors, itself and 1. 2 is an example of a prime number. It can only be, its only 2 factors are itself and 1. Only 2 will divide into 2, and only 1 will divide into 2. Actually, if we were to list the first 7 prime numbers, we would have 2, 3, 5, 7, 11, 13, 17, and so on. All these numbers being numbers that only have 2 factors, themselves and 1. They're only divisible by themselves and 1. Okay, and sometimes we're asked to express sorry, just noticed a mistake there, but sometimes we're asked to express numbers as a product of their prime factors. Okay, so if we were to express 80 as a product of its prime factors, then 80 expressed as a product of its prime factors is actually 2 to the power of 4 by 5. 2 is a prime number, 5 is a prime number. They're both factors of 80. So 2 to the power of 4 times 5 is 80, expressed as a product of its prime factors. How did we get that? Well, we looked at our list of primes, and we looked to see what would divide into 80, and 2 goes into 80 40 times. We look at the list again, 2 goes into 40 20 times. We look at the list again, 2 goes into 20 10 times. We look at the list again, 2 goes into 10 5 times, and then we have to say 5 goes into 5 once. So we have 2 times 2 times 2 times 2 times 5. That gives us 80 expressed as a product of its primes. Another example, express 36 as a product of its prime factors. Well, we look from our list above our prime factors, and we see that we divide 2 into 36, goes 18 times. We look again at our list from above and we see we divide 2 again into 18, we see that goes 9 times, and 2 won't go into 9 evenly, but 3 will, and 3 is a prime number and that goes in 3 times. So 36 expressed as a product of its primes is 2 times 2, which is 2 squared, multiplied by 3 times 3, which is 3 squared. Another way of expressing a number as a product of its primes, let's express 21 as a product of its primes, and we can do something similar in a similar way. We look at our list of primes and we see that 2 won't go into 21 evenly, 3 will go into 21 7 times. Okay, we look at our list again, see is there any other prime number that will go into 7 evenly, and we see that 7 goes into 7 once, and we stop there. And these are our prime factors. 21 expressed as a product of its prime factors is 3 by 7. Let's express 42 as a product of its primes. Well, we'll look at our list again and we can see that 2 will go into 42 21 times. From here we can see 3 will go into 21 7 times, and we can see that 7 will go into 7 once. So 42 expressed as a product of its primes is equal to 2 by 3 by 7. All the prime factors and multiplied together, they give us 42. So let's have a quick look at decimals then. Decimals, basically if we have a decimal here, this is the whole part of the number, this is the decimal point with the and bit, and this is the decimal part. And it's decimals are very much about place value, where the first place represents tenths, the second place represents hundredths, and the third place represents thousandths. Okay, so if we were to express a decimal as a fraction, then we need to look at the last place value before we specify what the value is in terms of a fraction. Okay, so let's go back to this one. Sorry, 678.226 is the same as 678 and 2 tenths plus 2 hundredths plus 6 thousandths, and actually that all boils down to 678 and 226 thousandths. Okay, so if we were to express 67.67 as a fraction, that's the very same as 67 and 67 100ths. We've 6, 7, 2 places, so we're talking about hundredths. Okay, 67.07 is the same as 67 and 7 hundredths, because we've 0, 7, 2 places, so we're talking about hundredths. 67.7 is the same as 67 and 7 tenths, 1 place, so we're just talking about tenths. And finally 67.007 is the same as 67 and 7 thousandths, because we have 3 places here, so we're talking about the thousandths place value. And we just think about rounding to 2 decimal places. How do we round? With a value like 69.367, that rounded to 2 decimal places is 69.37. How did we do that? Well, we look to see if this value here, if the third place after the decimal point, if it's a 5, a 6, a 7, 8, or a 9, then we increase this value here, the second place after the decimal point, by 1. But if the third value here is 0, 1, 2, 3, or 4, then it's do nothing. Okay, so 69.364, this is a 4, so we'll do nothing to the 6, it's 69.36. And just to quickly remind ourselves that to convert fractions to decimals, we simply, if we have a fraction 4 tenths, we simply divide 4 by 10 to get our decimal value. If we have 3 quarters, we divide 3 by 4 to get our decimal value. So let's look at scientific notation. Well, if you think about it, 10 is the same as 10 to the power of 1. And 10 to the power of 2 is 10 times 10, and that's 100. And 10 to the power of 3 is 10 by 10 by 10, and that's 1,000. So if we have 2.345 times 1,000, that's the same as, if you were to do it in your calculator, 2,345, where the 1,000 had the effect of moving the decimal point 3 places to the right. Okay? And we've said up here that 10 to the power of 3 is equal to 1,000. So we could rewrite 2.345 times 10 to the 3 being equal to 2,345. So we can write 2,345 in 3 different ways, as itself, or in this way here, or this way here. And this third way is through scientific notation, where the 2.345 is known as the coefficient, or the mantissa, and this part here is known as, the 10 to the power of. Okay, so if we were to rewrite this big long-winded number here in scientific notation, then we take the first digit, which is the 2, and we count how many places to the right before the number ends. We've 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's the same as 2.35 times 10 to the 10. And that's an easier way to write that big long-winded number. And similarly, if we have a very, very small number like this, 0.0000000203, then we can rewrite that by counting the number of places from the existing decimal point to just to the right side of the first digit greater than 0, but the digit that's between 1 and 9. So we say 1, 2, 3, 4, 5, 6, 7, 8. So that's 2.03 times 10 to the minus 8 steps that we took. Okay, so note only one digit to the left of the decimal point here, and here as well. So how do we add or subtract numbers written in scientific notation? Well, the rule is the powers, the 10 to this, must be the same. Okay, so if I have something like 3.769 by 10 to the 5 plus 4.21 by 10 to the 5, it's very straightforward. I just add this part of the number to get 7.979, and that's all by 10 to the 5. I don't actually do anything with these, but only note them here. Okay. On the other hand, the second example, I have 7.58 by 10 to the 5 plus 2.871 by 10 to the 6. I can't press ahead there. I must change 7.58 by 10 to the 5, so it's some value by 10 to the 6, and I do that by moving the decimal point one place to the left to give me 0.758 by 10 to the 6. Now I can add 0.758 to 2.871, which I'm doing here, and that's 3.629 by 10 to the 6. And it's the same method if you're doing subtraction. For multiplication and division, the powers do not have to be the same. For multiplication, we add the powers, and for division, we take away the powers. Okay, so if we have 6.3 by 10 to the 3 times 2.1 by 10 to the 4, then we multiply the two mantissas, the two coefficients, the 6.3 times 2.1, and that gives us 13.23, and then we add the 10 to the 3 and the 4, 3 and the 4 gives 10 to the 7, so it all becomes 13.23 times 10 to the 7. Similarly, let's look at a division 1 where we have 6.3 by 10 to the 3 divided by 2.1 by 10 to the 4. Notice these are not the same, doesn't matter. We divide 6.3 by 2.1, the two coefficients, and that gives us 3. And then we've 10 to the 3 divided by 10 to the 4. So we take 1 from the other, and that gives us minus 1. Okay, 3 minus 4 is minus 1. So our answer is 3 by 10 to the minus 1, which is the same as 0.3 by 10 to the 0. Okay, which is 0.3 by 1, which is actually 0.3. So if you just think about it here, let's rewrite it this way. 6.3 by 10 to the 3 is actually 6,300, and 2.1 by 10 to the 4 is 21,000, and 6,300 divided by 21,000 is 0.3, which is our answer here.